So we continue. We continue this morning's conference. With Tom Stoiber. I could not find the undergrad.
I did my undergraduate course. The University of Allen in Europe at the time. Also.
You were also the.
Yeah, I did my PhD.
So he's so Tom studied in Erlangen.
Yeah.
An undergraduate physics, I suppose.
Yeah, physics and mathematics.
Oh, physics and mathematics. Did the PhD with Hermann in Erlangen. He was a recipient of the Walter Benjamin Fellowship.
Yes.
And who went to work with Prodan.
Yeah, Emil, who everybody here knows, but who is suspiciously absent now.
I was worried about you and calling him. So and now he's at UC Irvine in the US. So Tom, please, the podium is yours.
Okay, so I'm talking about higher order topological insulators in K theory. So it's kind of a project that we did last year, or 2 years ago, I think, already with Emil and Danilo here. And so from the starting point, like from a perspective, of like this non-commutative geometry, phase theory approach to topological phases. At the starting point, we already understood many cases of topological insulators, right? There's like, just some vocabulary here. We have like so-called strong topological insulators, which have boundary states. Whenever you cut a boundary into the material, and weak topological insulators, which at least sometimes have boundary states. Then we need like crystalline topological insulators, and so on. So all of this can be described by one or other flavor of K theory. And so what's the big piece is what's kind of missing by the higher order topological insulators. So where you basically have like boundary states, not as flat bounds, but just when you cut like corners or hinges in your material. So that was like the outset. We wanted to understand also to see how we can understand this in terms of K theory. And so there's a bit of a recall. So what does actually both edge correspondence look like in 1 and 2 dimensions? So the edge states in 1 and 2 dimensions are simply so, as everybody here probably knows, if you have a 1-dimensional chiral chain, it can have topological end modes. So 0 modes localized at the end of a chain, and they correspond to, depending on what you want to call it, so physicists would call it the slack phase, probably. But a mathematician would say basically just the Toeplitz index of the off-diagonal part of the Hamiltonian. So 1-dimensional topological insulators, the chiral symmetry have like 0 energy end modes. In 2 dimensions, it's more interesting, right? If you have a material which has a non-trivial Chern number or Hall conductivity, then what you get is an edge following boundary currents. And what I want to point out is really it's not just like a qualitative statement that you have like, okay, so if you have like a topologically non-trivial system in the bulk, then you must have some kind of edge state. It's really quantitative, as in the bulk topologically invariant really gives you the number of edge modes. So that is like really a precise mathematical statement. So with that in mind, what are higher order topological insulators? As I said, so these would be states that don't have boundary modes at flat boundaries, but only when you cut like multiple boundaries, like 2 flat boundaries, and you make a corner. And it's very easy to see that these kinds of Hamiltonians must exist, because what you can always do is you can just take like a trivial insulator and you can decorate it with lower dimensional topological insulators. So you can just take like something on a honeycomb level and put as the very outermost layer, I can put like a chiral chain, which has a corner state. And then, of course, this corner state will still exist. This end mode of the 1-dimensional topological insulator really becomes a corner state in the 2-dimensional geometry. And whatever my bulk model is, I can just decorate it with as many of these surface layers as I want, and so make as many corner states as I want. So this gives what people call extrinsic topological insulator. So in this case, it's intrinsic second order topological insulator. The second order just refers to the codimension of the boundaries. In this case, the codimension of a corner is 2 in 2 dimensions.
Sorry, question.
Yes.
But if you add individual, states, that can only add an integer charge.
I mean, yeah,
For
for
this
sure.
to be topological, you want fractional.
No. So technically, so these corner states are protected, but they are protected by a common gap of the bulk and the surface model. Right? So unless you close the gap at the surface, you cannot remove this corner state.
But I thought you said you're putting them from,
I mean, I'm adding them on top, but I'm adding insulator layers on top. Right? So at the surface, there's still a gap, but it's only when you cut a corner you close it. So, but in any case, so what I wanted to say is that basically, morally speaking, you get this by decorating any insulator, and it has nothing to do with any kind of topology in the board. It's completely irrelevant what the board can have done.
That was my whole point.
Yes. That's why they are called extrinsic topological insulators. So, and in some sense, the problem is that these are very kind of uninteresting. In some sense, if you don't have any kind of symmetry, then basically every corner state arises in this form. Like it's just a trivial model decorated. So if you want to have something more interesting, we need to impose a symmetry. The very simple model is that we take basically the same geometry and we impose a mirror symmetry across the diagonal. In this case, this flexibility of just randomly adding surface layers disappears, because when we add an additional chiral chain in one boundary, then by the mirror symmetry, we have to add the same chain on the other boundary. So then if we add a chain which adds one corner state, then actually we always have to add 2 corner states. So that means that the change of boundary conditions can only change the number of corner states by an even integer. It means there's like one C2 invariant which is unaccounted for, and it turns out that in this case, this C2 invariant comes from a bulk topological invariant. So for these mirror symmetric insulators, what you can define is a mirror churn number in the bulk. And this mirror churn number modulo 2 gives exactly this parity of the corner modes. So this is an example of what we call a second order bulk boundary correspondence. So we really have a bulk topological invariant which determines that we must have a corner state. And so for materials of this kind, this is what we call intrinsic topological insulators, because no matter what boundary condition we take, we must have corner states. So those are the interesting guys. These are the systems that we want to classify. And we can also look at this stuff in higher dimension. So in 3 dimensions, it's a similar story. If we don't have imposed at least some kind of crystal symmetry, we don't have really intrinsic higher order topological insulators. Everything that we get, which has like hinge modes or corner modes, is just decorated trivial insulators, basically up to some sort of homotopy equivalence. But if we impose a symmetry, then we get the same kinds of symmetry constraints, that we can't just haphazardly add boundary layers. Because like if we have like a C4T symmetry or C2T symmetry, it's like if we add something on one side of the crystal, we have to add like corresponding images on the other side of the crystal. And then this gives again like the possibility to have protected hinge or corner states that you can't remove by changing the boundary condition. So for example, if we have like non-trivial classes for these inversion symmetric models, where you must really have like a current loop of edge current which flow around specific size of the crystal. And similarly for C2T and C4T symmetry, you must have hinge modes which flow around the symmetry relevant hinges, basically. So in each of these, these are very vaguely symmetry protected. Like there's a C2 invariant that you can't remove these boundary states completely. But they also don't tell you like exactly how many boundary states you have at which direction the current flows, what is the exact path that these current loops take, and so on. So it's a much less exact business than the usual like edge correspondence. So you could immediately say, okay, you have a churn number in the board, and this gives you exactly the number of edge states. So the second problem is that we need symmetry. And in particular, we need a very specific symmetry. And so in terms of K-theory, what we're supposed to use is twisted equivariant K-theory, which is a very, very complicated theory, unfortunately. The twisted equivariant the twist in this case refers to the fact that we need symmetries that mix real structures of complex conjugations with crystalline symmetries. Right, so for example, C4T symmetry composes time reversal and a rotation. So that makes a complex anti-linear symmetry or anti-unitary symmetry. So if you want to describe stuff like that in general, you need a bunch of data to describe the group action. You have an action of a group, and each element of the group can act either linearly or anti-linearly. So you have like an additional homomorphism phi, which tells you if a group element is basically unitary or anti-unitary. Then you can have a graded symmetry. For example, particle hole symmetry is an odd symmetry, so it's an off diagonal, so it's graded. And you can have, in addition, you can have twists, like you can have additional phase factors, like if you have fermionic symmetry, so both are distinguished by different twists. So there's quite a lot of data that you have to describe the group action, which makes the corresponding K-theories very difficult. But in principle, the definition of the K-groups is not so complicated. So in a very physically motivated way, one can formulate it like this. We take some C-star algebra of observers, and then this K group is really the group which classifies gapped self-adjoint operators, which are invariant under this relevant symmetry operation. And it classifies them up to homotopy. So we change this self-adjoint operator, this Hamiltonian, up to like stabilization with trivial degrees of freedom and homotopy. Basically, the equivalence class of the Hamiltonian is directly what this K group is.
Is this gamma index the sigma on top? Or?
Well, I mean, it was supposed to be this. Basically, this is was supposed to be an abbreviated notation. It's like, okay, so I have all this data, but basically you actually just have a group action. You can just subsume everything else into. Like you have some symmetry group acting on your K.
Well, you also need the twist, and so everything is in there.
Yeah, it's basically okay. That's it. So this is like this K0 group, which basically is by the definition classifies gap Hamiltonians in a certain symmetry. This comes with a companion. Oh yeah, that's what I forgot to mention. So this acts on matrix. Like you have additional finite degrees of freedom, like your internal on-site degrees of freedom also carry this representation data, right? Like you have like several atoms in the unit cell, and your group action can non-trivially act on the atoms in the unit cell. Then importantly, this comes with a companion theory, which is odd K theory. So we call it K1 or K-1, depending if you want to have indices go up or down. This is basically the group which classifies symmetric gapless Hamiltonians. Mathematically, those are Prodan operators, so operators which are invertible up the element of the algebra A. I mean, it is what it is. So it's basically you have two groups, one classifies gap Hamiltonians, one classifies gapless Hamiltonians.
And why gapless here?
So gapless, I mean, a Prodan operator is not gapless, it is invertible up to elements of algebra. So this kind of the Prodan operators are basically classifying obstructions to gap opening, right? the is equivalent to the index of this given platform operator. When we document it.
I admit I'm a bit lost because, okay, I mean, is this now for the, is this the dual part, the platform modules, or what should I think of this K minus one, or why do you measure that?
So basically, what do you mean by? I mean, I feel like you should understand this kind of stuff. But so I mean, you are all the people here, so I'm a bit confused. So no, platform. So it's basically there are two pictures. I mean, there are many pictures of K, right? I mean, you can basically describe the K1 groups as degree shifted.
All this I know,
right? So
that I was confused by the gapless. Why did it say gapless?
No, it's like because the equivalence relation on these operators does not involve not closing the gap, right? You're just preserving the Fredholm condition, but you're not preserving a gap. These will in general not have gaps. So, right? So mathematically, this is exactly what they do. So everything is confusing because basically actually K0 and K1 are kind of isomorphic in some sense, up to a suspension. But we still like to use very different representations in practice. Okay, so then these K theories form a homology theory. So particularly the way that we use bulk edge correspondence is that we set up algebra, which is that different parts of our system, and they should form an exact sequence. So the idea is that we have like some algebra observable, and so basically we look at elements that have on space of boundary, and we can go away from the boundary to recover a bulk Hamiltonian. And conversely, the part which lives at the boundary is some ideal, which I like to call E for edge states. And so K theory for these algebras as a homology theory, so it means that if you have an exact sequence, what you get is a natural boundary map, which gives you a long exact. So this is very abstract, and now comes basically the point why we find these K0 and K1 groups in this physical way, because basically what this boundary map does if you adapt these notations is just maps bulk Hamiltonians to boundary Hamiltonians. So you start in your bulk algebra with a gap Hamiltonian H, and then you take any pre-image of in your algebra, which is Hamilton split boundary, and then the equivalence class of that Hamiltonian is exactly what this boundary map gives. So it's an extremely trivial map if you formulate it like that. The key point is actually that this is well defined in the first place. So that's the magic of K theory, is that basically any pre-image that you can choose for your bulk Hamiltonian carries the same topological information, has the same K theory class. And the second thing is this is an exact sequence. So exactness means that we have a pre-image under the bulk class H, and the class of the bulk Hamiltonian H has a pre-image in this K theory class of A, so of our observer split boundary, if and only if this boundary map is trivial. Right? I mean, this is by definition what exactness means. Exactness means the kernel of one map is the image of the previous map. So we can use this boundary map to decide equivalently. Either we formulate it like this: the boundary map tells us if we can find a gap pre-image, or the other way around. This boundary map gives us the obstruction. So all of this is very, very abstract. So let's see how this plays out in practice. So this basically goes back to what happened. Hermann did with Johannes Kennendorf and Thomas Richter, who proved that basically these kinds of exact sequence mechanisms explains exactly full edge correspondence for quantum Hall systems. So for quantum Hall systems, you set up algebras where you have like a bulk algebra, which is like the group C star algebra of V2. Some people would call it just the continuous function of the torus. You have a half space system, which mathematically the tuplets algebra tensor some one-dimensional algebra of translation band operator. And you have an edge algebra, which is basically one-dimensional. So an algebra for observers at the edge, so it's a quasi one-dimensional operator. And in our formulation, what this boundary map will do is it takes bulk Hamiltons, which have non-trivial Chern number, and it maps it to gapless Hamiltonians, which have exactly the same edge conductivity as the Chern number. So this is kind of just the definition. So, and that is what it does. So the point is really that all of this is even well defined in the first place. So whenever we have a gap Hamiltonian with non-trivial Chern number, it gets mapped to some gapless Hamiltonian, which is independent of the boundary condition. And in conjunction with what I said on the previous slide, is that from a point of view of algebraic topology, what these edge nodes really are, they are just a symptom of the non-existence of clear measures. The fact that we can't take the bulk Hamiltonian, even in principle, and put it on a half space without closing the spectral gap means that there must be some manifestation in the spectrum, which in this case manifests as edge modes, which have a certain conductivity. Okay, so this is kind of the basic formalism, and this works for basically anything. You can use any kind of boundary effects, any dimension, any symmetry class. It just makes everything more difficult. So then the question is really, what is different about these higher order bulk boundary correspondences? Why don't we just like find some kind of exact sequence and then we set up this formalism, and then we have a boundary map which tells us like how many kind of corner states we get from this given boundary. And the answer is very simple. We could in principle, but it's too difficult. So as I said, the definition of this boundary map is very trivial. Basically, it is by definition just to put in a bulk Hamiltonian and it maps it to the class of the boundary Hamiltonian. Unless we stick into this formalism very specific exact sequences where we can compute these boundary maps by an alternative method, it's really hopeless.
Didn't Danilo do this, at least for examples?
I mean, yeah, if you have specific Hamiltonians, again, you can find three images there, you can compute the spectrum and everything, but that is extremely rare. So generally speaking, in this case, everything works because it's basically a tuplets extension or the Pimson-Wojciechowski exact sequence which is behind this. But if you stick in like more complicated geometries, maybe something like curved boundaries or even just a corner or something, then you get immediately lots of problems. So what we really need to do is break this down into solvable problems, which we can handle. So the formalism that we came up with for higher order bulk boundary correspondence really takes more input than just like a separation into like a bulk and a boundary. We want to have the data, more complicated data, we want to have a cofiltration of these algebras of a very specific form. So we want to have like an algebra AD, which describes a d-dimensional crystal. And then we subsequently forget more and more parts of its boundary until we eventually have just the bulk left. So forgetting stuff in mathematics, of course, means we take quotients by ideals. And so we quotient ideals of observers which live around certain boundaries of certain dimensions. So let's look at an example how this works in 2 dimensions. In 2 dimensions, we have 3 algebras. One, which, for example, describes Hamiltonians on a quarter plane. And at first stage, what we quotient out are observables which live at the corner of the Porter plane. So if you remove the corner, what we are left with are basically two infinite half spaces which are still loosely connected to the pole. So they just don't have a corner anymore. So then you can quotient out more because you still have boundaries left. You have the edges of the half space. So then you quotient out the edges of the half space, and finally you are left with just a translation variant of algebra of zones, which are the bulk. So that's kind of the mathematical setup now. It's like we have much more data because we want to distinguish between boundaries of different codimensions. So in 3D, similarly, we have sequences with three algebras, and the idea is that we quotient out successively the corners of the crystal, the hinges of the crystal, and the faces of the crystal. So now, the idea is that we do not basically push everything into the boundary map as we did for this easy example for edge correspondence, but instead we formulate bulk edge correspondence as a kind of lifting problem. We start out with a topological class of a bulk Hamilton, which lifts all the way over in the bulk, and we ask how far can we lift this K-theory class until we get stuck. And this really determines the order as topological. So what this means is, for example, if we start with a bulk Hamilton and we can't even put this on a geometry which has any kind of surfaces, then what we found is that we have a first order topological insulator which has surface states described by some K-theory class. So basically, when we get stuck at the first stage, then our surface states live in this K group of the surface algebra. If we can in fact lift to the geometry which has faces, but we get stuck in the next step, but can't. So when we can't lift to a geometry which has hinges, then we get the topological obstruction are the hinge state, and then we always get some sort of boundary states which are described in another K-theory class.
E2 is then the quotient of
E2 is the algebra described observable at the hinges of the crystal.
Is it a quotient of 8 by 8 1?
It's an ideal in 8.
Yeah,
Yes. And similarly, we can ask for third order topological synthesis. This is like finally we can lift all the way to A2, but not until A3. Then the obstruction somewhere sits in between. So then this gives corner states. And then of course the rest are trivial insulators. They do not necessarily have any states. So we can take this Hamilton, we can put it on the full crystal, and it's still gaps. So that means there are no boundaries. I mean, at least not in this sense. I mean, there can still be other stuff like this fractional corner state we talked about, but those are not the kind of corner states that I'm talking about.
So basically, you are like trying to compute a spectral sequence, right?
This is exactly the point. This is exactly the thing. So when we started out, we didn't understand nothing, but then we actually had to learn algebraic topology. So this was known to many people, just not to us. So the way that you compute these quantities of structures, exactly, you make a spectral sequence. And there are nice spectral sequences in K-theory which fit exactly to this cofiltrations. So basically, you get the first page, which are just K groups involving your ideals and the bulk algebra, and then basically successively you can compute page by page these boundary maps which give you at each stage the obstruction to your lifting problems. And basically, in terms of physics, you get these homomorphisms between sub-quotients of these K groups, and the co-kernels of these boundary maps are exactly what are the topological insulators of different order, and the images of these boundary maps describe the possible boundary states that you will find in your crystal. And from the way this is set up, the typical algebras that people use, those are basically finitely generated building groups. So in principle, you can compute all of these by solving enough spectral problems. Just find enough Hamiltonians, you diagonalize them, compute the boundary states, and so on. So in principle, you could always compute this. Now, of course, when I'm saying in principle, that's what algebraic topologists always say, right? It's like in principle, we can compute everything, but in practice, not so much. So, yeah. Okay, so then what I want to say is like, so we basically kind of accidentally rediscovered all of this, but of course, much of this was already known to physicists. The main difference is physicists, when they do this kind of computations, they don't use operator case theory, but instead they do, I'm actually not sure what they are doing. So certainly they are computing something which is somehow phenomenologically motivated, like they're modeling like the crystals by some sorts of manifolds and filtrations of manifolds. It's not clear why or if this has to give the same results as like our operator algebraic approach. I mean, there are good reasons why it's most of the time doesn't really matter that much what the actual computations are, because for these kind of spectral sequences, often what happens is that the first and second page are usually very combinatorial anyways. So most of the time, it doesn't really matter what you put in. There's only one natural way to get like boundary maps and so on between various things. So it's a good, most of the time their computations give the correct results, but it's not quite 100% clear, I'd say.
Do you go to the third page even, or?
I mean, if you want to go to corner modes. So it's not completely by accident that their approach works, but it's not very satisfying. So what we are arguing is we should really use the operator algebraic approach and really, like on the same footing as we do usually bulk edge correspondence, we should work with actual Hamiltonians, which are microscopic models, Hamiltonians which live on the Hilbert space, and so on, have actually computed edge states and so on. So we need models which we can, basic algebraic models for this kind of stuff. This is not so easy actually. Because these algebras, in principle, what they need to have are many properties. They need to live in the infinite volume limit of a crystal. So basically, the problem in case is always when you're working in finite volume, all boundary states are trivial because you're dealing with just a finite dimensional algebra. So what you really need is something which lives directly in infinite volume. But at the same time, we need to have something which has the same symmetries as a finite crystal. Right? I mean, as I had earlier this picture of this, like this cube with all the different hinges. If you want to figure out at which hinges you have which kind of states, you basically need to have something which looks like a crystal. So you can't just take like a single quarter space. But at the same time, if you take a single quarter space something, you don't have the symmetries of a real crystal because you can't implement rotation. And so you need to have like this rich filtration by ideas. So actually, these algebras that we need are like nothing that we had in the literature at the starting point. So we had to construct them also. And the idea that we use is to go back to this idea of, basically that's what I said. So basically what we need is an algebra which is got the infinite crystal which has boundaries, which is kind of paradoxical, right? I mean, an infinite cube usually doesn't have boundaries, right? If you take the both limits. So, but what I mean is this. We need an algebra which describes, roughly speaking, something like this. You take, for example, in 2 dimensions, you have a square crystal. What you want is to take the infinite volume limit. And depending on where your fixed point is when you scale up the crystal, what you might see in the infinite volume limit is either a corner, and then it continues infinitely in all directions. Or if you fix the position at a boundary in the middle or something, then it scales up to an infinite half space. If you're somewhere in the board, then it scales up to an infinite model without boundaries. So that's kind of the idea. So you look at different scaling limits of your crystal, where you keep different fixed points. And when you do this, you get different patterns, which are basically the building blocks of an infinite crystal, and you just need to glue them together, like a self-consistent model. And what we found was the ideal tool for this is what some people call pattern equivariant Hamiltonian. So Emil, who is not here now, calls this Galilean invariant Hamiltonians for some reason, but always gives us trouble with the referees. The more canonical term of pattern equivariant Hamiltonian. So this is an idea which comes originally from the study of quasi-crystals. It was introduced by Jean Balisard and Werner Scanlon. It is kind of described like algebras for Hamiltonians which live on a quasi-crystal and kind of preserve this ergodic translation invariance of the quasi-crystal. So what you really want to have basically is you want to have a relation. The Hamiltonian is not just one Hamiltonian on one single Hilbert space, it's really a relation which takes as inputs different patterns, and for every pattern spits you out a physical Hamiltonian from Hilbert space. And so the input is a collection of patterns which has some invariance of the translations. Like if you have one pattern in your collection, then you can also shift it by every lattice side of the pattern. And then you have some algebraic conditions for consistency. It should be short range operators. There needs to be a translation variance. So if you shift the pattern, it should shift all your matrix elements by the same amount. So basically, if you take one pattern and you move it by 10 lattice sides, then you get the same Hamiltonian just shifted by 10 lattice sides. And finally, you need some kind of continuity condition that the Hamiltonian depends continuously on the pattern. So it's very abstract, but in practice, what it looks like is this. You have some kind of algorithm. The Hamiltonian is some kind of algorithm which takes as input a pattern and it populates correctly the pattern with matrix elements. For example, you put in a quarter space or a half space or full, and the pattern equivalent Hamiltonian, it fills in the correct atoms and bonds at the correct places. Like in this case, in the bulk, we get a black atom, and at the boundary, we get a red atom. And because we're using the same rule, no matter which pattern you put in, we always get something which self-consistency looks basically as if everything is part of the same crystal. So that's kind of the idea for our algebras. Exactly, we want to basically we want to have something which for every pattern that we can find in the infinite volume limit of a crystal gives us a Hamiltonian, and they have to glue together from self-consistency. Now, mathematically, if you want to really work with these algebras, there's an alternative representation more useful. There's a starting point. You first have to give these patterns a topology. So as I said, one of the conditions for pattern equivariant Hamiltonians is that the Hamiltonian depends continuously on the pattern. Now, of course, a pattern is a discrete subset of R, really, generally. And we need to put up topology on this end. That is possible. So people have used many topologies actually for this. Our favorite topology is the so-called fell topology. But most people don't really know what it is. So equivalently, one can describe this in terms of what's the so-called vague topology and the set of Prodan measure. This is what the formation of Balisard and Cantor originally. But really, if you want to understand visually what these guys what this topology actually means, is you should really take the Hausdorff metric on the d-dimensional sphere after taking the stereographic projection. So I'm just going to show you as a picture what it actually means. You take half of a lattice in 2 dimensions. And so okay, right, so you take half of a lattice and you map this to a 2-dimensional sphere. So then this covers basically half of the sphere with some lattice points. And if you shift the position of the lattice to infinity, then this covers more and more of your sphere. And so then if you use like the notion of the Hausdorff metric, then really what these half patterns do, they converge to the full two-dimensional lattice when you move to infinity. So very visually, we can tell this is the correct topology for our problem. Basically, when we want to glue different boundaries together at infinity, what we need is exactly something like this. Like so that the continuity with respect to the pattern tells us basically no matter how we approach the bulk limit, for example, continuity must guarantee that we get the same bulk chemical. It's kind of the idea behind using this topology. And then if we have a topology on the space of patterns and an action, then there's a basically established algorithm to get an algebra. What you do is you define a groupoid algebra. The groupoid, for those people who don't know, it's something like a group, but only with a partially defined operation. So you can't multiply any two elements, but you can only multiply compatible elements. But that is still good enough to define a sort of convolution multiplication. So in our case, we have our étale groupoids, which are somehow defined as input by a collection of patterns and so on, and which gives us technically a convolution algebra. And if we take this convolution algebra and complete it in the C-star norm, we get a C-star algebra.
There's no twist here.
We could put a twist, but we don't have one. So that is technically abstractly, this is a C-star algebra. The way it relates to this idea of pattern equivariant Hamiltonian is really that this algebra has representations of all of the constituent patterns. So whenever you have a pattern in your collection psi, you can make a representation of the Hilbert space. And the matrix elements of these representations have all these properties that we put for pattern equivariance. So we can really say that this groupoid algebra that we constructed realizes this idealization, this idea of pattern equivariant observable. So we took basically this vague idea of pattern equivariant observables and put it into something very concrete, which is a groupoid algebra. And it's not just any groupoid algebra. Actually, these are very nice. So these are basically Morita equivalent to cross products. So we understand it very well, especially we can compute their K-theories and so on. It's not a hopeless problem. So this is the ideal formulation for our the ideal starting point for our classification problem.
Just a question: who proved that this is Morita equivalent to cross product?
Everybody knows this. No, it's because by construction, this is an abstract transversal of a transformation groupoid. And so this is, I think this formalism of abstract transversals is already in Renault's original work. So basically, if you have an abstract transversal of some groupoid, then it's implements the Morita equivalence. Yeah. But yeah, I mean, you have to figure out how these things work, of course, if you want to compute things and correct this. Okay. So let's just briefly look at some examples of what this formalism gives. So the very simplest example is that we take as input just a single pattern and we look at its orbit as a translation. So then this gives us a collection of patterns which may have different accumulation points. For example, if you just, very easiest case, you just take the lattice CD and look at its orbit and the translations. Well, it's a translation invariant pattern, so the orbit just contains a single pattern. So then the groupoid algebra simplifies tremendously. It's just the group C-star algebra of CD itself. And this is going to be what the bulk algebra is. If it has start with a pattern which has no boundaries, then you just get an algebra of translation invariant observables. Then the next The next example is a discrete half line. So if we start with something which is just n, so just basically a one-dimensional half line, then what we get under the orbital translation is basically similar to the picture I showed earlier with the stuff on the sphere, is that you get the orbit of the pattern itself, but you get a new accumulation point, which is basically the infinite lattice. And then the associated groupoid algebra is actually exactly this Toplitz algebra. And with this, our formalism recovers basically the special case of the bulk edge correspondence that I had like on one of the earliest slides. So everything is self-consistent. The next dimension, the next example, if you go to some stuff which has corners, what you have is basically a quarter plane. So a discrete quarter plane is mathematically n times n. And then you actually have many accumulation points. You get basically in the orbit of the pattern, what happens is if you Emil drew these very nice pictures. And okay, so visually, the way that the pattern topology works is you stand at some point and they move in a certain direction, and eventually, if an observer starts at the corner of the quarter space and walks around one of the edges, eventually what you will see is just a half space or a half lattice. And similarly, if he walks along the other edge, he will see another half lattice. Whereas if he walks in any other direction inside the book, he will eventually see a full lattice. And this gives exactly like the structure of these accumulation points of the orbit. And this gives us the unit space of our group, which is a topological space. But mathematically, what we get is still what mathematicians call the quarter plane Toplitz algebra. So this is also another known algebra, just another representation of it. Now, finally, if we want to go back to our idea of looking at infinite crystals, where we take different patterns and glue them together, what I do now is I take these pictures earlier, where I take the different patterns from the infinite volume limit of the crystal, and I number them. And basically, we take all of these patterns and we glue them together into one groupoid. So we make a transversal. This like by taking basically the orbits of all of these patterns together. And then the magic is that this gives us a filtration of unit spaces and respectively transversal. And we can filter like our sets of patterns by grouping them by different boundaries, different dimensions of boundaries. Like we can make an algebra which has just the half space, we can make an algebra which has just the corners, and so on. And this is exactly like this, gives exactly this ideal structure that I had earlier when we were discussing this cofiltration of algebra. Right, so the summary is, we have a very concrete construction. We basically take as input a d-dimensional crystal, which kind of looks like a polytope. You make out of that an algebra, and basically you get a cofiltration where you look at boundaries of different dimensions. And the point of the matter was everything is equivariant with respect to the symmetry of the crystal. So this gives us exactly the algebras we were looking. Okay, so that is unfortunately just the starting point of the problem. Right. Because what we now need to do actually is start computing things. Because I told you, well, basically, all these boundary maps are just very trivial. Actually, the mathematical definition of any of these kinds of boundary maps is just take a Hamiltonian, put it in a certain geometry, and then look what their boundary states are. But it doesn't tell you which Hamiltonians to look at and how to compute anything. Especially what we need to do for classification problem is we need to find all generators of the bulk K theory group, which is a twisted equivariant K group. Figure out what the different generators are, and at the end of the day, for every kind of for every K theory class, we need to take one example and compute what boundary states we get. So basically, for every generator of the K group, we need to find one solvable example Hamiltonian where we can actually compute what the boundary states are. And for physicists, this is easy. Because the physicists can just put it on a computer. As a mathematician, this is unfortunately not allowed. It's illegal. And the referee will not allow it. So for the physicists, it's okay. We can compute everything in principle now. For mathematicians, we have a big problem because we don't know how to diagonalize Hamiltonians to live on an infinite quarter plane. So the trick that we came up with was what we call the adiabatic approach. So it turns out that you can actually make a very nice approximation of these groupoid algebras by just using commutative these algebras that affect the topological spectrum. So basically, you can, similar to the way that we just constructed our algebras for infinite crystals by gluing together patterns, we can similarly glue together something which looks like these algebras, but there's just CW complexes glued together. And one can then show that there are maps on the level of K-theory, which basically go from some kind of topological K-theory of these approximations to the actual K groups of our algebras. And because we have a commutative diagram, all of these are compatible with these boundary maps. So that means we can compute at least some of the boundary maps on the topological side. And then we know that if we do the computation of the full operator algebras, we get the same result. So with this trick, we were able to compute it with some boundary maps, for example, for C4T and C2T symmetry. So it's basically the example that we had at the very beginning. Right, with these kinds of corners, we can prove that these hinge modes are real in our operator algebraic models because we can prove that we have like boundary maps which map like some fault generators. Basically, you take the Burke generators as non-trivial Chern-Simons invariant, and then you can prove that you must always get hinge modes like this in our operator algebraic model. So this is how we actually compute things in practice. I mean, analytically. Of course, if you're a physicist, you can put it on a computer. Okay, so that was all of it, basically. So as I said, the point is we have formalism now. Principle, how we can compute things in practice, it's still very difficult. Especially because for the most part, many of the examples that you need are like C4T symmetry and C2T symmetry and so on. It's actually very recent that anybody has been able to compute the K theory. I mean, So there are very few tools actually available to do these computations systematically. So if you want to actually classify like relevant amounts of symmetry groups, there are still many things we need to figure out. But at least I think we have the right tools available now to answer this question on the operator algebraic level. Yeah, so that's
Questions?